Hi there, this is Dr. Matthew J. Traum from Engineer Inc. The ultimate purpose of this series of videos is to set up a simple example static stress strain simulation using the ANSYS finite element software package. I am not a computational guy. I'm an experimentalist. And so I'm always very skeptical of finite element solutions given by computers that aren't backed up by some sort of calibration or some sort of hand calculation. So I'm going to describe for you in this series of videos a process that I would actually go through to do one of these simple calculations and then verify it. So what I'm showing here in this static image is the model system of interest. These are sample coupons from PASCO. These happen to be made out of aluminum. The one on the bottom here is what they look like initially straight from the manufacturer right out of the package. They are clamped into a stress strain apparatus here and here, and a force is applied. The force causes them to elongate first elastically and then deform plastically and ultimately rupture. So this one here on the top, you can see there's actually a failure located right there. That's as a result of an applied force causing elongation and ultimately the achievement of the ultimate tensile strength for the material. So what we're going to do in our model is we're just going to look at the rectangular portion of the sample coupon. So essentially where this fillet ends, this whole length, to where this next fillet starts. And the reason for that is because the cross-sectional area here is quite a bit bigger than the cross-sectional area here. And so the force that's imposed on this sample coupon is really concentrated into this thinner region. So we're not going to worry so much about the elongation in this portion, at least for our simple ANSYS model. We know that from the spots that I pointed out, from the end of this fillet to the end of this fillet, the distance is measured to be about 80 millimeters. We also know that the sample coupon is about 4 millimeters wide and about 0.9 millimeters thick. So what I'm going to do first is go through a hand calculation to describe if I clamp this thing down and I imposed 100 newtons of force, what the elongation would be. And then in follow-up videos, I'm going to show you how to put this geometry into ANSYS and impose those boundary conditions and run the simulation, and we will compare the hand calculation that I do in this video to the ANSYS results that we get in subsequent videos, just to make sure that everything is working as expected. So let me put this picture away, and what I've prepared is just a sheet of paper here, and I can run through the calculation that I would do by hand so that you can follow along and see what I'm doing. So let's start out with the rectangular portion of the sample coupon, not necessarily drawn to scale, but just to give you a sense of the shape. So again, we said that these guys measure 80 millimeters from one fillet to another fillet, and their width is about 4 millimeters. And the thickness, that's the thickness into the page, is about 0.9 millimeters. Okay, so those are the critical dimensions. Now, what I do when I run these things in a real experiment is I clamp them down and then I impose an external force. So I'm going to just draw a symbol here that indicates that I've clamped this end so that it can't move. And on this side, I'm going to impose a force of 100 newtons. Now, if you've actually run the experiment, you know that the PASCO stress strain apparatus can impose a force on the sample of up to 250 newtons. So 100 newtons is a pretty modest amount, something that's definitely achievable by the PASCO stress strain apparatus. So my goal is, given this geometry and knowing that the material is aluminum, given this force imposed on known sample material of aluminum, the goal is to determine the elongation. So how much this sample elongates as a result of this imposed force. So to do that calculation, I need a few material constants. I need the Young's modulus, which I can look up for aluminum, which in this case is 7.1 times 10 to the 10th pascals. And I'm also going to need the yield strength, which is 2.8 times 10 to the 8th pascals. That's another value that I can look up for this material. Okay, so in order to get to this goal of my elongation, given this geometry and these material constants, the first thing that I'm going to do is calculate the cross-sectional area upon which this force is acting for this geometry. So the cross-sectional area is just the width times the thickness. So the area is the width times the thickness. We know the width is 4 millimeters. We know the thickness is 0.9 millimeters. And I'm going to add a conversion factor. I know that for every 1 meter, there's 1,000 millimeters. And if I square that, the end result here is going to have units of square meters, right? Because this millimeters and this millimeters cancels with the 2 millimeters there. The reason that I'm doing that is because all of my stresses are in pascals. Pascals carry units of newtons per meter squared, and so I want my area in meters so that I can do a multiplication without having to make additional unit conversions. So if I do this calculation, what I end up with is 3.6 times 10 to the minus 6 square meters. So that's the force, that's the area upon which this force is acting. So my next step is to determine the stress that's imposed across this geometry. So we know that the stress is equal to the force divided by the area. And the force, as I said before, is 100 newtons, so that value I know. And the area, which I just calculated, is 3.6 times 10 to the minus 6 meters squared. And if I carry out that calculation, what I end up with is a value of 2.78 times 10 to the 7th pascals. So that's my stress. Let me put this in a box because that's an important value. Now here I need to do a sanity check. I mentioned in the introduction to this video that we are looking at the elastic, not the plastic region of the stress strain curve. So we're not going to drive this system to failure. We're just going to impose a force on it, and it's going to deform elastically. Presumably, if we remove the force, it would then return back to its original shape. And so what I need to do is compare the stress that I've imposed on this geometry with the yield stress. This is the stress at which I essentially leave the elastic region and enter the plastic region. So if you remember a stress strain curve, looks like this. And the curve goes something like that. This guy right here is approximately the yield stress, and this region here has a linear slope. That slope is the Young's modulus, and provided I am to the left of this dotted line, I am in the linear region where I have elastic deformation, not plastic deformation. What that means is if I load the member and then unload the member, it essentially goes back to the original length. It doesn't plastically deform and assume some longer length as a result of the force that I've imposed. So what I'm checking by comparing this number to this number is that I am in fact in this region to the left of the dotted line. So let's do that comparison. So this value, which again corresponds to that mark that I made on the graph, is 2.8 times 10 to the 8th pascals, and this value, which is the stress that the object actually experiences, is about 2.8 times 10 to the 7th pascal. So what that means is I'm actually way down here on the stress strain curve, definitely to the left of this dotted line. So that's good. I'm in the elastic region, so I can continue with my calculation. So again, my goal is to get the elongation, and so we will use now the definition of the Young's modulus, which is the stress over the strain. I know that elongation has something to do with the strain, so I'm going to reorganize this thing using some multiplication manipulation. So the elongation, the strain is just the stress divided by Young's modulus. I know these values, right? This guy is this value, and this guy is this value, the Young's modulus that I looked up at the beginning of the problem. So I'll put in those known values, 2.78 times 10 to the 7th pascals, divided by 7.1 times 10 to the 10th pascals. And when I do the calculation, what I end up with is 3.91 times 10 to the minus 4. No units, right? Because pascals cancels with pascals. So this is a unitless value, which is okay, should not be surprising, because what I'm calculating here is the strain. And remember, strain is just an elongation divided by an initial length. So this is essentially a length divided by a length. It should be unitless, and so no surprise that there are no units here. That's actually good. I've done the calculation correctly if I've ended up unitless. Now what I'm going for, of course, is elongation, because that's my initial goal. So I need to do some mathematical manipulation here, multiply the initial length by the strain, and that's going to be equal to the elongation, which is the goal. This is what I'm shooting for. So if I put in numbers, well, I know that my initial length, I said, was 80 millimeters, so that's 0.08 meters. Again, just doing the conversion, keeping everything in meters so that it's consistent. And the strain, which I just calculated, is 3.91 times 10 to the minus 4, again, unitless. And if I carry out that math, what I end up with is that my elongation is 3.13 times 10 to the minus 5th meters. So let's put that in a box, because that is the actual goal. That is the result that I was looking for. Remember, the goal was elongation, and here is the value. This happens to correspond to about 31.3 micrometers, so that just gives you a sense of how small this elongation actually is. But this is the number that we will be looking for in our ANSYS calculation, 3.13 times 10 to the negative 5th, which again is the elongation of this object, the PASCO sample coupon made out of aluminum. If I impose 100 newtons on it and clamp one side so that that side does not move. Okay, so now that we've done this calculation, we will wrap this video up. In the next video, I'll show you guys how to set up the same geometry using ANSYS finite element software, and hopefully, if we do everything right, we will be able to verify this value using our ANSYS model. Okay, thanks for your attention, and I'll see you in the next video.